All right, guys. As promised, more volumes of revolution using the Warscher method with our big R and our little r, so our large radius and our inside radius, where we're subtracting the two to get rid of that missing middle section. And this time we'll look at volume revolved around other things besides an x-axis or a y-axis as well. So here's the first one. Here's an application problem. So a manufacturer drills a hole through a small metal sphere of radius 5 inches. The hole has a radius of 3 inches. What's the volume of the resulting ring? So we've got this, we had a sphere here that was 5 inches in radius, and we took a drill and we drilled straight through it. Now you might think, well, it's just the volume of the sphere minus the volume of the cylinder, but then you'd be missing the little caps here. So you'd be missing a little bit of roundness on each edge. So what we want to do is we want to come up with an equation, right, for the outside sphere here in just 2 dimensions. And that equation would be just the area of the equation of a circle would be x squared plus y squared equals 5 squared. All right, so it's centered at 0, 0, radius is 5, there's our circle. So if we just want to look at, say, the top half of this, we could solve this for y, and we get y equals, so this would be 25 minus the x squared, and the square root of that. It actually would be plus or minus, but the top half would be plus. So that's the equation for this top half of this circle. And then we would be rotating that around, and then we would be taking out this part at 3. All right, so here's another picture, if you want, of just the cross section of what's happening right in this section right here that we're going to rotate around. So we end up with an outer radius of this big R of this function, right? Our square root, the circle, basically. And then we're going to subtract from it this other radius, which is always just 3. So this distance here from the axis up to what we're drilling out is 3. So what we end up getting is that our volume will equal pi times the integral from, so if we see where they cross, it actually crosses from -4 all the way to 4. So we're going from -4 to 4 of the big R, which is the square root of 25 minus x squared, minus the little r, which is 3 squared dx, because these little sections are going along the x-axis. All right, and we can actually make this a little easier if we want. So if we notice that it's symmetric, we can cut it right in the middle, which is horribly drawn there, and we can say it's just this area doubled. So we could say this is 2 times the area from 0 to 4 of the square root of 25 minus x squared quantity squared minus 3 squared, which is just 9, like that. So we can square this out. 2 pi, the integral from 0 to 4, 25 minus x squared minus 9 dx. So that'll be what, 16 minus x squared? So that's, when we integrate that, we're going to have the 2 pi out front. We'll have 16x minus x cubed over 3 from 0 to 4. So now we're just plugging in 4. So we get 2 pi. 16 times 4 is 64. 4 cubed over 3 is 64 over 3. And then if we plug in 0, we get 0. So it's just going to be that guy right there. If we want to simplify that, we can, but there's our answer basically right there. All right, which is not exactly the same thing as if we just took the volume of the circle and subtracted the volume of the cylinder that we cut out from it. All right, it's actually a little bit different. All right, another example. Find the volume of the solid, and I'm going to switch colors because I'm tired of being red. Find the volume of the solid created by rotating the region bounded by the graphs of y equals -x squared plus 8, y equals 4, around the line y equals 1. All right, so I don't have a picture for this. We got to try and draw this. So I do suggest trying to draw a picture on all of these. So we've got that. So maybe that's crossing up at 8, and it's a parabola opening down. All right. So this is y equals -x squared plus 8. We've got the line y equals 4, which is probably right around here. And we're going to rotate around the line y equals 1. So we got another line right here, y equals 1, and we're going to rotate around that. So basically we're taking this region here, and we're rotating it over here. I mean, that's a bad drawing because the middle should be on that. I'm going to fix that. There we go. So now this is going to here, and this is going around here, like that. So we've got an outer radius, our big R here, which is going from this line, y equals 1, all the way up to this curve, which is that line. So this distance here, the bigger radius, big R, will be this curve, negative x squared plus 8, minus this 1 here. All right, it's the distance between the two, so we just subtract minus 1. And this little radius here, of this guy, is going from 1 to 4. So our little radius is 4 minus 1, or just 3. So this one I could probably simplify a little bit. So that's negative x squared plus 8 minus 1, or negative x squared plus 7, I guess is what that one becomes. All right, so we could integrate now. The whole thing would be from here to here. Or we can say, okay, it's symmetric, and we can just go from 0 to where they cross here. All right, so it's going to be, and to find where they cross, we would have to set these two equal to each other. So we need to set 4 equal to x squared minus, or sorry, negative x squared plus 8. Subtract the 8. Cancel out the negatives. Take the square root. X equals 2. So they're going to cross here at 2, and they would cross back here at negative 2. But we can just go from 0 to 2 and just double it because it's going to be symmetric. So our volume here is doubled pi times the integral from 0 to 2 of big R, that guy, minus little r, that guy, squared dx, like that. All right, so now if we want to, we can work this out by hand. We'd have to square this guy out and then combine some like terms and whatnot. Or we can go to our calculator. Remember, we know how to integrate on our calculator. So let's practice that. So we go to math, and it's number 9. All right, I'm going to leave off the 2 pi for now. I just want to know what this is. So we're going from 0 to 2 of the quantity negative, down at the bottom, x squared plus 7, close parentheses, that guy squared, minus 3 squared was 9, and x is our variable. So we're getting 49.0666666666. Math, enter, enter. So there it is as a fraction if we want it. I'm not sure if that's really any better. Maybe we could just subtract 49 from it. And then change it. Oh, there we go. 1/15. So it's 49 and 1/15 times 2 pi. So this 49 times 2. What is 49 times 2? What is that? 98. So it'd be 98. And 2 times 1/15 would be 2/15 pi. And there's our answer. All right, so we use the calculator from here to here. We kind of, I mean, maybe it's cheating, maybe it's not. Depends which section it is on the AP exam. All right, but we do need to be able to do things on our calculator to make things go a little faster. Next up, another problem, new color. Find the volume of the solid creating by rotating the region bounded by the graphs y equals the square root of x minus 5, y equals 3, x equals 4, and x equals 2. So let's try and draw this. So the square root of x minus 5, so that means if I plug in 5, I get 0, and then it looks like the square root of x graph, which kind of goes up like that. The line y equals 3, so maybe that's here. The line x equals 4, so that's going to be somewhere back here, 4, and x equals 4 is just going to go straight up and down. So maybe I should be labeling these. X equals 4, this one was y equals 3, this is y equals the square root of x minus 5. So it looks like this is our region here, and we're going to rotate that about the line x equals 2. So here's x equals 2 back here. And that's what we're rotating this around. So we've got this region bounded by that curve, and that curve. And it looks like we're going from 0 to 3, and we're rotating this around this line here. So this right here is going to be my inner radius, right there. And my outer radius is going to go all the way to that function, from there to there. So here's my little r, and here's my big R. So little r is probably the easier one here. Little r is, this is 4, this is 2, so it's 4 minus 2 is 2. My big R is this function minus 2. All right, but this function, well, we'd be making little washers going up the y-axis, basically. All right, so we want this in terms of y, because we're going to be integrating dy, and we're going to be going from 0 to 3. So like our volume is going to be pi times the integral from 0 to 3, because our washers are going up the y-axis. We're stacking them up that way, or our discs are being stacked up as we go up. All right, so we're going to be integrating dy. Our little r is going to be this 2, so minus 2 squared, and we need to know what the big R is. All right, so the big R is from this curve minus the 2. All right, because from the curve, it would just be the whole way over. But we want to know the difference between the two, so it's this curve minus 2. So this curve is this x minus 2. But that x, we got to square both sides, and then add 5, and that would get us what x equals. So we're getting y squared plus 5 minus 2, or y squared plus 3. So we get y squared plus 3 quantity squared for that one. I don't know if you could tell, I just had to take a little max break there. So we just paused and restarted again because Max was whining. All right, so let's see. Back to this guy. So now we got to try and integrate this. So we can square this out, or we can type this all into the calculator. I'm going to probably go with the calculator here just to practice more calculator stuff. So there's our calculator. Oh, just turned off. It wasn't quite fast enough. All right, and we're going to math and then number 9. And we're going from 0 up to 3 along the y-axis. Our function, all right, we can use y, or we can just use x's, is going to be x squared plus 3, and I'm just using x everywhere I've got y, quantity squared, minus my little radius is going to be 2 squared, or 4. And I used x as my variable because I switched everything over, so there we go. 117.6. So we get 117.6 pi. There's our answer. All right, or you can say 117 3/5 pi. All right, either one of those is fine. All right, so there was some more applications and more practice with rotating and finding volumes for revolutions. And I think there might be one more here.